So welcome back, everybody, to another day of calculus. So we're going to be starting with this new topic. Generally speaking, we're going to be looking at a bunch of applications of the derivative. So now that we've defined it and understood what it is, and the first thing that we're going to study in detail is really going back and looking at comparing a function to its tangent line, and then using the tangent line to approximate the values of that function. And so this process is called linearization. And we'll see examples of why you might do this. But the basic idea is that functions are complicated and they're hard to work with, but lines are not complicated and they're easy to work with. So if you just need some approximate information, sometimes it's easier to look at the tangent line of a function and look at the value of the tangent line instead of looking at the value of the original function. To dive into this a little bit more, before going to the chalkboard, let's look at some Desmos stuff. So this class is about the study of differentiable functions. So let's look at like y equals x squared. Give you an idea of what I'm talking about. So the kinds of applications that we're going to do, you're going to take like a particular point on the graph, like let's say that x is equal to 2 and therefore y would have to be equal to 4. That nice purple point there. And you can also look at the tangent line through this point. And we've had some practice calculating what the tangent line is going to be and then using slope-intercept form to write that down. So if you want the tangent line at the point 2, 4, you would take the derivative of y equals x squared, and then you would plug in x equals 2. So you'd get 2x, plug in 2. So the tangent line goes through 2, 4, and has slope equal to 4. I'll write that down here. So like y minus 4 is equal to the derivative, let's call this, I'll keep it in function notation. So I'll say f prime of 2 times x minus 2, even though we know this number is equal to 4. So when you look at a function and compare it to its tangent line, when I say that near to the point 2, 4, the black line is going to be similar to the green function. Like you can kind of see that. Like if you're far away, the tangent line and the function are not very good approximations of each other. But if you zoom in on that point, then what you're going to see is that there's basically no difference between the original function and the approximating line. So why not just use this linear formula instead of using x squared? So that's the idea of approximation. And so this process is called linearization. So you're replacing the original function with its tangent line. And you can do this at any point. So you could do this you can linearize around any point. So you could do this at 0, 0. And you could draw the tangent line at that point, which we know should just be the horizontal axis, but let's see that. So like y minus, what did I do? So y minus 0 equals f prime of 0 times x minus 0. In other words, of course, I've just written down y equals 0, because we're at the point 0, 0, and the function has 0 derivative there. And I claim that when you zoom in on this point really far, there's really not going to be a difference between the function and the line. So let's test my claim. We zoom in far enough. I mean, here we had to zoom in a little farther than we did the previous time. But I think if we go far enough, there's to our eyes, there's going to be essentially no difference. Zooming in. And so this looks like about the scale at which there's no difference. So if you're operating on a scale of like 0.005, what's that, 5,000ths? Then there's essentially no difference between the function and its tangent line. So this is like a reasonable interval in which you could replace the function with its tangent line and still get valid results. Later on, we'll have to be more careful about how to estimate the error. The error would be the difference between the tangent line and the function itself that I was sort of mousing over there. And for any differentiable function, that is to say any function that has a tangent line, you'll always be able to pick a point, zoom in, and the function will be essentially equal to its tangent line as you get closer and closer. The interesting thing is that if you pick functions that are not differentiable, correspondingly this won't be true. So like the classic function that's not differentiable is the absolute value function. So I mean, this is differentiable at every single point except the point 0, 0. And it's a cool exercise to check this. Basically, the left-hand limit is -1, the right-hand limit is +1 when you're looking at the difference quotient. They don't match, so the limit of the difference quotient doesn't exist. Intuitively, this has constant slope -1, this has constant slope +1, so there's no way to get those two slopes to match and have a single tangent line. And the geometric way of understanding that is now, sorry about that. The geometric way of understanding this is now if you want to zoom in at the point 0, 0, and you can even write down what you might think would be a reasonable tangent line. Like y = 0 is probably your most reasonable guess for a tangent line, because remember when you had like g of x = x squared, which doesn't look altogether that unsimilar to, which doesn't altogether look that different from absolute value function, at least if you're in this interval. So that tangent line was the purple line. But we're not looking at x squared, we're looking at absolute value. This is not differentiable at x = 0. So zoom in on this. Let's at least go out to the scale of 5,000ths. But look at what's happening. It's getting nowhere close to that purple line. In fact, this is kind of awesome. No matter how far I scale in, it looks exactly the same, doesn't it? Like I'm here at the level of 5,000ths that I was before. If you weren't looking at the scale on the axis, you'd think that this was the original picture without zooming out. In fact, this little V shape is a scale invariant shape. You keep zooming in, and the picture stays the same. It's kind of amazing. And so this is reflecting the property that this function is not differentiable at that point, and it's never going to be well approximated by a tangent line. So we can't do tangent line approximations to functions that are not differentiable, which is just, I think, kind of a cool point and worth talking about. And so I'm glad that I can show you this visualization. I'll start introducing some formulas now, but before I do, let me give you a chance to ask any questions or make any comments. Okay. So I'm just going to write down the equations that go along with the visualizations that we've just kind of explored. So you're looking at a function, and I'll go ahead and even draw the same picture. Like look at this nice quadratic, and I used x equals 2 before, but let's just take x equal to a. And here would be a f of a on the graph. So I'll write down this formula in general, but you can keep in mind what we did with the quadratic. And you can approximate with the tangent line. I think I like to use different colors normally, but they don't always show up very well on the camera. Draw this tangent line through the point. And let's use L of x for the tangent line. And there's an implication here that the tangent line is taken at the point A. You choose a point A first, and then you write down L of x. And so this is just going to be, what's the formula for L of x in y equals mx plus b? What I was writing down before was y minus y1, so that's like y minus f of a. And I was setting that equal to the slope, which was f prime of a, times x minus a. So you can see that's where, you can see how this formula would change if I used a different point a. And what I'm going to write down here is just formula for y equals L of x. And so just solving for y, you would see that the answer is f prime of a times x minus a plus f of a. And so this has a name. It's called the linearization. The orange line is the linearization of y equals x squared at the point x equals a. And the formula for the linearization is the tangent line. So really there's nothing new here. It's just finding a tangent line, and now we're calling it a different name, linearization. We're calling it that because we're going to use it to like approximate the value of the function. I'll bring in some, or remind you of some other terminology, like we had this notation delta x for x minus a. We're going to bring in this notation delta f for f of x minus f of a. And so again, just to keep on emphasizing, you pick the point first, and then you've got the tangent line, the linearization. You've got delta x representing your change in like your x value, and delta f representing the change in the function f, or the change in the y value. I mean, the way you should think about this, I've written x equals a here, which is true, but let's just look at the point, sort of label that as the point A, and now I'm sort of freed up to think of x as the variable. So in practice, you're going to be picking some other number x, and then this distance, I mean, if x is bigger than a, it's a distance. If x is less than a, it'll be like the negative of the distance. But this interval you think of as like delta x, representing your change from your fixed point A. And then what's delta f? So if you go to your y values, so here's a and here's f of a. And where is f of x? So f of x would be like up here. So if you want to think geometrically like I like to do, then your delta x is this change on the x-axis, and your delta f is the corresponding change in the function. And what we're going to be doing as an exercise, throughout the class is we're going to be approximating delta f with the corresponding change in the tangent line. So what's the corresponding change in the tangent line look like here geometrically? Well, you walk at the same point x, and you walk upward to the other point on the line. And f of a is the same point on the function as it is on the tangent line. The tangent line is, of course, designed so that when x is equal to a, the value is f of a. But on the tangent line, you have some slightly different points. So let's walk it over. And what's this orange distance? So what's the distance between the two orange points? So that's the change. That's the y value at x minus f of a, right? So this yellow length is actually given by y minus f of a. I mean, y equals L of x, right? So, so here's L of x, and I'm subtracting f of a. And so what is all of this telling me? It's telling me that if I want to take delta f and approximate it with the tangent line, that's going to approximately be f prime of a times delta x. So that's the theory part. That's the theory part. The rest is all just going to be applications. So let me let you kind of stare at that and parse it for a second, and please tell me if you have any questions. So there's a question about which part represents y in y minus f of a. So y is equal to L of x. So you should think of y as being this formula. So this is just saying that L of x minus a is equal to f prime of a times x minus a. Or L of x minus f of a, excuse me. So here's your L of x and here's your f of a. And there are other ways to appreciate this or derive this approximation formula. Here are some other ways to contextualize it. One way is to say that from our graphical exploration, we've kind of figured out that f of x is approximately equal to its tangent line. So approximately equal to L of x, which is f prime of a times x minus a plus f of a near the point x equals a. So near. This was our graphical exploration because we were zooming in, zooming in, zooming in, and the function got closer and closer and closer to the tangent line. So when you see me using these squiggly equal signs, that's what I mean. They're approximately equal, at least under this condition. And then if you now subtract f of a from both sides, you'll get this formula that delta f is approximately equal to f prime of a times delta x. And the second way to see it is remember that f prime of a is a limit of a difference quotient. F prime of a is a limit as x goes to a of f of x minus f of a over x minus a. And what I'm going to do is I'm going to erase the limit and replace it with a squiggly equal sign, because the derivative is literally equal to the limit. But if instead of taking a limit, if I just consider x to be some fixed number close to a, they'll no longer be equal, but they'll be approximately equal because of what a limit is. It says that as x gets closer to a, this difference quotient will get closer to f prime of a. And of course, this is just delta f over delta x. And now if you multiply both sides by delta x, you get the equation that delta f is approximately equal to delta x times f prime of a. So that's sort of three ways of understanding it. One way, the function is close to its tangent line. The other way, through the definition of the derivative. And the third way that I like, because I like geometry, is just drawing the picture of the function and the tangent line, drawing delta x, drawing delta f, and then drawing the approximation, and just sort of noting that as long as x is close to a, your approximation will be close to delta f. Okay, cool. So let's do some examples. And I will do some book examples here just because I think they're really good and worth talking about. Let's do the following. So the question says, take the cubed root of 8.1. I know you can get this in a calculator and get a good approximation, but so the question is approximate how much bigger? How much bigger the cubed root of 8.1 is compared to the cubed root of 8. And anything else? And use the result to approximate the cubed root of 8.1. So approximate how much bigger the cubed root of 8.1 is compared to the cubed root of 8, and use the result to approximate the cubed root of 8.1. So this is a linearization problem, and working with students over the years in office hours and tutoring sessions, the number one thing that students say when they are given a problem like this is, I know the linearization formula. They'll tell me, like I know that delta f equals f prime of a times delta x, or not equal, excuse me, but approximately equal. But then they say, like, how do I use this to do that problem? They say, I don't see a function here, so I'm not sure what to plug in to what. And I do want to acknowledge that in some sense the difficulty in problems like this is not so much applying the formula or plugging into the formula, but it's figuring out like how to use the formula in the context that you're given. And so how might we figure that out organically, you know, other than me just sort of immediately writing the answer down? So we're approximating how much bigger cube root of 8.1 is compared to cube root of 8. So in other words, I want to approximate the difference, right? I want to approximate the difference. So what I'm seeing is that this might be my delta f. I know that delta f is f of x minus f of a. And which point, you know, do you want to be x, and which point do you want to be a? I think you always want to set up your model in such a way that if you can, that your point a is the thing that's easier to calculate. So cube root of 8 is equal to 2. So I'm thinking a is equal to 2. I'm thinking x is equal to 8.1. Remember, in this model, x needs to be a value that's near the point a, which is certainly the case here. And it's looking like my f of x is going to be the cubed root of x, or in other words, x to the 1/3. So that's what I'm starting to see from thinking about this problem a little bit, and I'm getting that from the clue that I'm looking at this difference, and I need to think of that difference as like a delta f. So then I just have to put together what function do I want to choose. The cubed root function makes sense, and then, well, there's x and there's a kind of given to us. And now to do the problem, I can say, well, this is approximately equal to f prime of 8, right? Oh yeah, I said a equals 2. I went ahead and did the cubed root in my head. A is equal to 8. Sorry about that. Because it's f of x minus f of a. And so this is going to be approximately equal to f prime of 8 times delta x, which is just x minus a, right? So 8.1 minus 8. So this is going to be approximately equal to f prime of 8 times 0.1. So that's just f prime of 8 over 10. And I'm going to be done as soon as I can figure out what is f prime of 8. So if I know that f of x is the cubed root of x, what I should do is I should calculate f prime of x, which is now going to be, by the power rule, 1/3 times x to the minus 2/3. And then once I calculate this function, I can now plug in x equal to 8. You wouldn't plug in 8 first and then take the derivative. If you plug in 8 first and then take the derivative, you'll get that the derivative of a constant is 0, and all your answers will be 0 to all these problems. So don't do that. Figure out the derivative function first and then plug in the value that you want to find. And so let's go ahead and do that. F prime of 8 is 1/3, and so x to the minus 2/3, that's 1 over x to the 2/3. So that's going to be 8 to the 2/3. So the cubed root of 8 is 2, and then 2 squared is 4. And there's, yeah, so I'm just getting 1/3 times 1/4 equals 1/12. So I'm getting 1/12 divided by 10. And therefore, the cubed root of 8.1 is roughly equal to the cubed root of 8 plus 120, or 1 over 120. And so that's how much bigger it is, approximately. And use the result to approximate the cubed root of 8.1. Well, that's just taking the value of the tangent line. So that's just taking L of 8.1. So you can either plug that into your formula for the tangent line, or you can get it in the following way. So this is going to be 2 plus 1 over 120. So how did I figure that out so fast? I'm remembering the formula that I used to do this calculation in the first place. It was f of 8.1 minus f of 8 is approximately equal to this. So since it's, right, so f of 8.1 minus f of 8 was approximately equal to 1 over 120. So then it must be true that f of 8.1 was approximately equal to f of 8 plus 1 over 120. So that's 2 plus 120. But by all means, you can plug this into your formula for L of x, and then that's what you'll get. And let's actually compare this to some Desmos work. Let me check my answer. So we were investigating f of x equal to the cubed root. Just looks something like that. And we were looking at the points x equals a equals 8, and then the y value would be 2. So we were trying to approximate delta f. So delta f is f of 8.1 minus f of 8. And that's it's roughly equal to 0.00829 whatever. And our linear approximation said that it should be sorry, I got to turn off notifications. And so our linear approximation said this should be roughly the same as 1 over 120. Let's see if it is. So 1 over 120 is 0.0083 repeating, and the actual difference is well approximated by 0.0082988. So our linear approximation was actually very close to the actual difference. In terms of estimating, so what's the cubed root of 8.1? 2.00829. And of course, 2 plus 1 over 120 will be 2.00833. So this, it's telling us that this linear approximation is pretty cool. For me as a young student, I was pretty excited by this because you're not really going to be taking the cubed root of 8.1 in your head. But it's just really kind of a cool concept that you can still get those values, as long as you stay close to a value that like cubed root of 8. You can still get the values of the function. All right, any questions or comments on that before moving on to another example? Next one, let's do some interactivity. So so please find this function L of x for f of x equal to root x times e dx minus 1 and a equals 1. So in other words, please linearize this function at the point a equal to 1. So go ahead and work on that for a couple minutes, and then we'll discuss. And chat me any questions. Okay, after giving you some time to work, this one I won't work out all the details explicitly because I know we've already had some practice, like using the product rule and using the chain rule. So this is really sort of like restating. It's asking a question you're familiar with, but in a different way. So it's basically saying find the tangent line to f of x at the point a equal to 1. And so I will show that to you graphically. So if we go over to Desmos here, you can see the plot of the function. And at the point a equals 1, you plug in 1 to see that f of 1 is equal to 1, and there's the point there. And so you want to find the tangent line, and I typed it in here, but in f prime of 1, I calculated to be 1.5. I showed you that as well, that when writing the equation in the form y equals slope times, I guess this isn't exactly mx plus b, it's y equals slope times change in x plus f of 1. But this is the tangent line that you're getting. And it comes from calculating the derivative, plugging in 1, and then using the 0.11. And then if you wanted to approximate f near the point 1, like if you wanted to figure out what's the value of f of 1.1, you could instead like plug in, like I could call this like L of x. You could instead plug in L of 1.1 and get, you just get the correct answer up to 2 decimal places. Of course, if you use like a significant figure, it's only accurate to 1, because this would be, this should have been like 1.16. But it's still pretty close. So that's what we're going for here. And by the way, there's this concept called the error. I briefly mentioned this before, but didn't write it down. So that's where you take the like the absolute value of the difference. So like f of 1.1 minus L of 1.1. So this, and you put absolute values around it, so that it's always positive. In this case, the error is like 0.009. So it's just the difference between the function and the approximation. And oftentimes more important than the absolute error is the relative error, or the percent error. So comparing the actual difference to the value of the function. So as a percentage, this is something like 0.7% error in our calculation. And the reason why you use these numbers is like it tells you as a percentage how far away you are from the actual. Because if L of 1.1 were equal to f of 1.1, then it would be like 0 over this, which would just give you 0% error, which is kind of what you're looking for. Okay, and just to kind of write that down, so it's not just an example. Yeah, there's a question. Can I show how to compute f prime of x? I can show how to do that too. Yeah, but just to finish up this, this statement. So we look at the error, which is the difference between like the actual value and the approximate value. And you can look at the relative error, or the book calls this the percent error. And that's going to be, well, you would just take the error divided by the actual value, which in this case would be what? Like absolute value of x. And then if you multiply that by 100, then you'll get the percentage. So like by what percent of the actual value are you off by? And yeah, how to compute this derivative. Using the product rule, it's the derivative of root x first, so that's 1 over 2 root x times e to the x minus 1. So the product rule says it's derivative of the first term times the second plus the first term times the derivative of the second. The derivative of e to the x minus 1 is e to the x minus 1. And then you use the chain rule and multiply it by the derivative of x minus 1, but that's just equal to 1. So that's my formula there. And then plugging in the number 1, I'm going to get 1/2, and then square root of 1. E to the x minus 1 is 0. E to the x minus 1 is e to the 0, which is equal to 1. And then I'm adding to this the square root of 1, which is 1, times e to the 0, which is 1. So I'm getting 3/2 for f prime of 1. And that's consistent with what I plugged in. Okay. Any other questions or comments? I'll just leave you with one more small remark. So we've seen delta f is approximately equal to f prime of a times delta x. And if you use y equal to f of x, then you would rewrite this as like delta y is approximately equal to f prime of a times delta x. And you'll see people use the following notation. You'll see people write dy equals, f prime of a dx. So this is like what people call differential notation. That's just if you don't like writing the squiggly equal sign. If you want to use an actual equal sign, we just change the notation a little bit. And this is just to help you understand that a small change in x would produce so how can I say this? So if a small change in y is equivalent to a small change in x times the derivative. So it tells you how x and y are related on a very small scale when you're really, really zooming in. And some people drop the use of the a there, and they will just go ahead and write dy equals like f prime of x dx. And this is like a scientist shorthand notation for telling you that if you want to calculate small change in y by small change in x, you have to multiply it by the derivative at that point. If you're using Leibniz notation, it gets even better because you get to write that dy equals df dx times dx. So scientists and physicists love this notation because actually, since y equals f of x, I'll just use dy dx. So scientists and engineers love this notation because it's so easy to think about canceling literally a fraction. It's a limit of difference. That's just one way to keep this approximation idea straight in your head. So different ways of notating the same thing. Okay, so we can talk a little bit more about that at the top of the class next time. Thank you everybody for your time and attention. We'll see you on Monday.